get going with that. And now we'll do screen share. Because there's all right, there's Hartree material to review. Okay, good. All right. Yeah, so I'm going to, I've got a few minutes here. I'm going to review where we ended up last time. It was, there's actually quite a lot of material. So what we accomplished last time was mostly working through the Hartree theory. So let me go over this. The Hartree theory is a variational approach to a multi-electron system. We're considering an atom here. I call the trial wave function phi, capital Phi with an H. The capital letters are used for wave functions of the entire atom, whereas the lowercase letters I'll use for individual electrons. Anyway, the H here stands for Hartree. And it's basically a product of a series of single particle orbitals, one for each electron. I'm using these parenthesized letters here to indicate the electrons, and inside the kets, I've got a label of the orbitals. That's the notation we'll use. So this amounts to having a certain set of orbitals distributed amongst a certain set of electrons. Now the word orbital here refers to a single particle wave function. So the multi-particle wave function here is a product of single particle wave functions, one for each electron. I'm going to try to use the convention of Latin indices for electrons to go from 1 to n, and Greek indices like mu and lambda that go from 1 to n for orbitals. Each one of the orbitals that appears in the Hartree trial wave function is assumed to be a product of the spatial times the spin part. The spin part is assigned a magnetic quantum number, m sub s sub lambda equals plus or minus a half. We just assign those at the beginning when we're setting up this trial wave function. There's no loss in generality in doing that, because each s sub I sub z is actually a good quantum number of the Hamiltonian. As far as the spatial part is concerned, it's associated with a wave function I'll call u sub lambda of r. Lambda here again refers to the orbital. U sub lambda of r, which is just the usual scalar product. And it's those orbitals which are the variational parameters of the Hartree method. The Hamiltonian consists of two terms. They're called H1 and H2. H1 is the terms that involve only the coordinates of one electron at a time, which is the kinetic energy and the potential energy of interaction with the nucleus. Whereas H2 involves the inner electron potentials, which takes the coordinates of two electrons at a time. In fact, it's just the sum over pairs of electrons with the Coulomb denominator. So we need to compute in accordance with the variational principle, we need to compute the expectation value of the Hamiltonian with respect to the Hartree state, which is up here. And this turns into a sum of two terms. One is a sum over integrals I call I lambda from 1 to n. And I've got somewhere here, is it here? No, it's over here. I've got an integral summary page. So here's the integral summary page. The integrals I lambda here is can be thought of as the energy of orbital lambda due to the kinetic energy and the energy of interaction with the nucleus. That's of course not all there is, but that's a contribution to it, and we call that I lambda. So the contribution from H1 here, the first term in the Hamiltonian, turns out to be the sum over all the orbitals of these I lambda integrals. Now, as far as H2 is concerned, which is the inner electron potential energy, when you work that out, sandwiching phi Hartree around that, what we get is we get this expression. It's this one half the sum on lambda and mu, excluding the diagonal elements where lambda equals mu, of integrals that I call j lambda mu. And to go back to the integral page, here's the j lambda mu integrals. These are called direct integrals. And in fact, these are the same type of direct integrals we saw earlier in our perturbation theory of helium. And they have the physical meaning of being the mutual electrostatic energy of two electron clouds associated with orbitals lambda and orbitals mu. That is, the square of the orbitals gives you the probability density. In atomic units, you multiply by -1 to get the charge density. So what we basically got here is a charge density of particle lambda or orbital lambda times the charge density orbital mu at different spatial points r and r prime divided by Coulomb denominator and integrated. And that's in electrostatics, that's the mutual energy of the two electron clouds. It's the energy required to bring the electron clouds rigidly from infinity into their final location, and is therefore a positive quantity. We talked about that earlier in the perturbation theory of helium. Anyway, that's what the J's are. So the expectation value of the second term is just the sum of these J's excluding the diagonal elements. The diagonal elements are excluded because they would represent the self energy of the electron cloud, and we don't expect that to contribute to the equations of motion or anything else. I mean, it's the self energy is not included in the standard Hamiltonians. So this means then that we end up with a functional, which is used in the variational principle, which consists of the energy functional, which is the first term, minus another term, which is the Lagrange multipliers. Lagrange multipliers here are used to enforce the normalization of the single particle orbitals. Since the spin part's already normalized, it really just means a normalization of the wave functions. And these are given in terms of integrals n lambda, which n just stands for normalization. So here's what they are. They're the obvious normalization integral. And anyway, so this gives us f. And then when we carry out the variation of this, we want to vary with respect to both the orbitals u lambda and their complex conjugates. Those two equations give us equivalent equations or complex conjugates of each other. So we just vary u lambda star. And if we do this, then we end up with the Hartree equations, which is summarized here on a third sheet, which is over here. And here's what they are. And this is basically where we ended up at the end of the hour last time. Hartree equations consist of a set of pseudo Schrodinger equations, one for each orbital, u lambda. It looks like a Schrodinger equation because it's an operator, Hamiltonian operator, kinetic plus a potential, plus another potential, acts on the orbitals u lambda, which you see here and there, and gives us an energy times u lambda. Now the energy here is actually the Lagrange multiplier for the constraint. So it appears in the interpretation of an energy eigenvalue of this pseudo Schrodinger equation. This leaves open the question about the relationship between these energies epsilon lambda and the energy estimate of the variational principle. That's something that's discussed in the notes. But in any case, I'll call this a pseudo eigenvalue, pseudo energy eigenvalue, and this whole thing is a pseudo Schrodinger equation. It's not a real Schrodinger equation for the reason that the potential V lambda, which is due to the inter-electron interactions, is given down here, and it's given in terms of the orbitals themselves. Thus, this equation, in spite of appearance, is not a linear equation because the V lambda depends on the orbitals. In fact, it's quadratic in the orbitals, and therefore this term is really cubic in the orbitals. And so these are the Hartree equations, and they are mathematically rather complicated. They amount to a system of coupled integral differential equations for the unknown orbitals u lambda or u mu, ranging from lambda equals 1 up to n. Now, these potentials v lambda, which are included in here, have a simple physical interpretation. And that's important to keep in mind because they might be mathematically complicated, but the physics is actually quite simple. The physics is that this v lambda of r, if you can think of r here as a field point, is equal to the electrostatic potential produced by all of the other electron clouds. The other ones means we sum on mu not equal to lambda. So we sum over all the other electrons, we square the wave function for electron mu, that gives us the charge density times, well, we're using atomic units, so the charge in the electron is -1. So the probability density times -1 is the charge density. So except for a sign, that's the charge density up there, evaluated at not field point, but source point r prime, divided by Coulomb denominator and then integrated over the source. So in electrostatics, this is nothing but the electrostatic potential at field point r due to the charge clouds of all the other electrons except for electron or orbital lambda. And that's the potential which appears there. And so what we see is that u lambda is an eigenfunction of the Schrodinger equation in the potential, which has to be determined self-consistently. That's to say, it's determined by the orbitals. So this is really a collection of n pseudo-Schrodinger equations is a system of coupled integral differential equations. And you can't solve it by the usual methods for solving the Schrodinger equation in which someone gives you the potential, because when we start, we don't know what the potential is. The potential has to be determined self-consistently on the basis of the solutions, the orbitals u lambda. So there is the very real question of how does one even solve this? But in any case, as I say, the physics of it, I think the physics is clear. And I think it's quite interesting that this physics comes out of this simple product form for the Hartree trial wave function. Okay, so that summarizes, it took me about 10 minutes to do it. That summarizes where we ended up at the end of last hour. So before I go on any further, starting new material, are there any questions about that before we go on? Because it's going to be important to understand this in order to understand the following steps. Any questions? All right, if no questions, then we will proceed. I think the first question is, how the heck does anybody solve these system of coupled nonlinear equations? And the answer is use a method of iteration, which I'll now describe. It goes like this. The first thing I'll draw it as a flow chart. The first thing is we do is we guess the orbitals u lambda of r. Now, how do you guess orbitals? Here's one possible procedure for doing it. One can use what's called the Thomas Fermi model of the atom. We haven't discussed the Thomas Fermi model. I have a set of notes on it if you want to read about it, but I think for lack of time, I probably won't lecture on it. Let me just describe it briefly, however. In the Thomas Fermi model, the electron cloud is treated as if it were a fluid, an electron fluid, which is governed by the equation of state of a degenerate electron gas at 0 temperature. This is a topic which is discussed in all introductory courses in Stat Mech. And so I assume that you all know what I'm talking about. This is where you have a Fermi C and you fill the electrons up to the Fermi C. And one can derive an equation of state. It only applies at temperature T equals, well, you can correct it for higher temperatures, but the simplest case is T equals 0. In that case, the equation of state is a relationship between the pressure and the density. In any case, this electron fluid is a negatively charged fluid, which hangs around the atom because of the positive charge of the nucleus, but it also repels itself. And so one creates a kind of a spherically symmetric distribution of charge, which in many respects is like the distribution of matter in a model of a star. It's governed by a combination of hydrostatic equilibrium, balancing of the forces on the fluid elements. Those are electrostatic forces combined with pressure gradients. Those balance out. And ultimately, they give rise to a set of coupled nonlinear equations for the potential, the charge density, and the pressure as a function of radius. And these can be worked out. So if you solve the Thomas Fermi model, what you get is a potential energy. Depends on the number of electrons and nothing else. And the nuclear charge depends on those two things and nothing else. So you get a density. You get a potential. It's a rotationally invariant, so you can solve the Schrodinger equation in that central force potential and obtain orbitals u lambda of r. Those could be taken as your initial guess for the Hartree theory. So this is a bit of a digression to explain where this guess might come from, but that's a way of doing it. Now, once we've got the guess for the orbitals, then what we do is we use those orbitals to compute the self-consistent potential. We compute the v lambda of r. By the way, something to mention that I should have mentioned up here in connection with the Hartree equations is that the potential v lambda depends on which orbital it is that you're talking about. And the reason is because this self-consistent potential excludes the orbital from the electrostatic potential. We don't expect electrons to be acted on by their own electron cloud. That's not physical. They're acted on by the other electrons. So that's why we exclude the mu equals lambda in here. What that means is that this sum depends on the orbital lambda, which this potential is driving in the pseudo-Schrodinger equation. Is also, as I mentioned, there's really a collection of n of these. There's n of these for the different orbitals. And this v sub lambda is different for every one of the different Schrodinger equations. So in effect, there's a collection of Schrodinger equations which have different Hamiltonians, not because of these terms, which are the same, but because of that term, which is different for each orbital. All right, in any case, we compute the v lambdas then. And then what we've got is we've now got the V, we've got V's for a bunch of Schrodinger equations, which we can now solve for as if they were linear equations for the orbitals U lambda. So we solve them, except let me put some dots in here, leave some space in here because I'm going to fill in something later on. So what we do is we solve for the orbitals U lambda of R, like this. But then what we do is we say, how do they compare to the original orbitals? In particular, we look to see if they've converged. So we put in a converge question here. I don't know if in computer science classes they teach you about flowcharts. They did when I was a student. But anyway, here's what we do. When we say if the convergence answer is no, we loop back and we compute via lambda again and we iterate like this. Whereas the answer is yes, then we're done. And what we've got is we've got a set of self-consistent orbitals, U lambda, and also self-consistent potentials. But we also, by the way, have the pseudo eigenvalues, the epsilon lambdas. We've got all of that. Now those things can then be assembled. The wave function is just obtained by multiplying the orbitals together, the multi-particle wave function, and then the Hartree-Fock estimate for the energy can also be computed from the orbitals. So we get both the usual things from the variational principle, an estimate of the energy and an estimate for the ground state wave function. Now, so this is how this works. Now, the way that I've set this up, it becomes necessary to solve these pseudo Schrodinger equations for a given potential V lambda at each stage of iteration. And these potential V lambda of R in general is not rotationally invariant. That's why I put a little arrow over the R, which is in there. Of course, the potential of interaction with the nucleus is rotationally, it's a central force potential, but this one is not. And the reason is because there's no reason why this sum of these orbitals here should add up to give you a rotationally invariant potential. So in other words, these are really fully three-dimensional Schrodinger equations and you can't separate variables. Now, three-dimensional Schrodinger equations are a lot harder to solve, general three-dimensional Schrodinger with lumpy potentials, than are central force problems. So Hartree suggested a simplification of this procedure, which is to add an extra step in this flowchart in which the potential V lambda of R vector is replaced by potential I'll call V lambda over bar of R scalar, that's without the arrow on it. And I'll define this down here. Is V lambda of R scalar is equal to the integral over solid angle of V lambda of R vector. In other words, it's just the angle average of the self-consistent potential, which is computed in step number 2 of this flowchart. By integrating over all angles, what we create is a new potential, which is a central force potential. And that means that in this stage here of solving for the orbitals, we're solving central force problems. And as we know, those reduce to radial wave equations, which are just one-dimensional wave equations. So it's much easier to solve one-dimensional problems than it is three-dimensional problems. This was true in Hartree's day when things are done by hand, but it's still true even now with modern computers. So this is still a nice thing to do. Anyway, if we do this, then the orbitals U lambda, which emerge, are central force orbitals. And so they're characterized by the usual central force quantum numbers in L, M sub L, and also there's an M sub S, spin quantum number. All right, so this is mostly what I want to say about Hartree's theory. Now, as I mentioned earlier, the magnetic quantum numbers that are associated with the individual orbitals are just assigned at the beginning of the procedure, up or down. And as I said, in principle, there's no loss of generality in that, because by assigning different values, you can ultimately assemble the solution you want. Now, on the other hand, the energies that come out, if you look at this, don't depend on the spins, the assignment of the spins. The procedure here just involves the spatial parts of the wave function. And on the other hand, we know that in a multi-electron atom, the energies do depend on the spin. We saw this in helium, where the ortho states were lower in energy than the para states for otherwise equivalent quantum numbers. The reason being is that the ortho states have higher spin symmetry, namely symmetric spin states, and therefore lower spatial symmetry, that is to say antisymmetric spatial states. And the antisymmetric spatial states means that the electrons are kept far away from one another, further away from one another, and this lowers the Coulomb energy. So this is the mechanism whereby the spin state affects the Coulomb energy of a system of electrons. And this carries over to multi-electron systems. In fact, it's a basic physical principle that carries across all of multi-electron physics. So it's worthwhile keeping in mind. So in any case, we know that the energies depend on spin. So why doesn't it show up here in this Hartree picture? Well, the answer is that the Hartree trial wave function is not properly anti-symmetrized. It's a product of single particle orbitals, but there's been no attempt to anti-symmetrize it. And therefore, this is an example of a wave function that lives in what we called earlier the nominal Hilbert space, but not in the physical subspace of the nominal Hilbert space. That is to say, the subspace of states which satisfy the symmetrization postulate. So really, they're not even physical states. That's one thing to say about them. Why did we do it? Well, we did it because why did Hartree do it? Because of simplicity. All right. So no wonder it doesn't reveal the physics that only follows from the symmetrization postulate and doesn't reveal that physics. So as a result, was almost as soon as Hartree's paper was published, Fock went to work to improve it by incorporating the symmetrization postulate. And I think the rest of the lecture tonight is going to be taken up with what's called Hartree-Fock theory, which is a generalization of Hartree's theory, which is designed to incorporate the symmetrization postulate. I have to say that otherwise, Hartree-Fock theory is very similar to Hartree's theory. Number one, it's variational. Number two, it deals with multi-particle states that are composed out of products of single particle orbitals. Number three, the spin states, the spin parts are just assigned up and down. And number four, the variational parameters are the spatial parts of the wave function. All that's the same as in Hartree's theory. What's different is that the wave function is properly anti-symmetrized. So let me start with the Hartree-Fock trial wave function. I'll just call this a phi here without an H subscript. So no H subscript equals Hartree-Fock. That's going to be my notation here, the Hartree-Fock theory. So here's the Hartree state, and what is it? It's defined this way. There's a normalization, which is 1 over the square root of n factorial. I'll say something about that in a minute. And then the rest of it is a determinant. There's a determinant where you have orbital 1 for particle 1, orbital 1 for particle 2, running across the first row to give you orbital 1 for particle n. The second row is orbital 2 for particle 1, orbital 2 for particle 2, and so on going across. Going down, we go down here to orbital n for particle 1, and going across, we go to orbital n for particle n like this, filling in an n by n matrix, or really it's a determinant here like this, determinant of single particle orbitals. Now, I'll say something about the single particle orbitals in a moment, but let me say, first of all, this is called a Slater determinant. Is the name of what this is called, Slater determinant. I don't know how Slater and Fock talk to each other, but Fock was using Slater determinants for his analysis. If you expand out the Slater the determinant using Cramer's rule, what you'll get is a collection of n factorial terms. And what these n factorial terms, how they differ from one another, is that the n orbitals that appear here they are 1 through n coming down a column, are permuted. All possible permutations of those orbitals amongst all possible electrons are contained in the n factorial terms. And then the terms are multiplied by plus or minus signs, depending on whether the permutation is even or odd. Now that's just the definition of a determinant, but that's what he set up, Slater set up. The reason for doing that is because we want something to satisfy symmetrization postulate. I'll say more about Slater determinants and symmetrization later on, but right now let me just comment that if we swap the orbitals, 2 orbitals, that would be like swapping, let's say, the first 2 rows of the Slater determinant. By the rules of the determinant, that changes the sign. So this is what you want for a physical state consisting of electrons, is that if you swap any 2 electron orbitals, the overall state should change sign. So phi changes sign upon any such swap. So this is set up in such a way that phi is a physical state. It satisfies the symmetrization postulate. It is not a single product of single particle orbitals, but a linear combination of n factorial such products. All right, so this is the Hartree-Fock state. Now the individual orbitals themselves are just like in the Hartree theory. They're a spatial part times a spin part, ms lambda. and the ms lambda is set equal to plus and minus a half, we can think of just doing some distribution of up and down spins to the various n orbitals when we start the calculation. Later on, worry about other values of those spin quantum numbers. So we do that. The spatial part is associated with the spatial wave function, r u lambda scalar product. Let me write it correctly here. This is u lambda of r. And as in the Hartree theory, these are the variational parameters. Those are the things we want to solve for. All right. Now then, what else to say about this? Yes, here's something else to say about this, about some of the properties of the Slater determinant. The Slater determinant is obviously, just by the way I wrote it down, it's obviously determined once the single particle orbitals are determined. You just put them in the matrix and multiply it out. But the question is whether or not the Slater determinant is unique. There's uniquely determined by the set of single particle orbitals, and the answer is definitely not. It's not uniquely determined, and the reason is the following. Let's do the following. Well. So first of all, I mentioned earlier that if I swap two of the orbitals, that phi changes sign. There's a few more comments to make about that. If two of the orbitals were identical, that's swapping two columns. If orbital 1 and orbital 2 were identical, then we'd have a Slater determinant in which two rows were identical. And according to the rules of determinants, the determinant would then vanish. This actually is a version of the Pauli exclusion principle. It says if you put two electrons in the same state, well, Pauli says you can't do it. A better way of saying it is you can do it, but the answer turns out to be 0. The multiparticle wave function vanishes if you do that. You can actually see that more generally, if you make any row or any column for that matter of a Slater determinant linearly dependent on the, or linear combination of the other columns, rows or columns, again, the Slater determinant will vanish. Along those same lines, let's take these single particle orbitals lambda, and let's create new ones, which I'll call lambda prime, which are just linear combinations of the old ones. So let me write it this as a sum on index lambda times some matrix I'll call C lambda lambda prime, like this, where the matrix C should have a non-zero determinant because we want non-singular linear combinations. So let's just rearrange the single particle orbitals by forming linear combinations, non-singular ones. Question is then what happens to the Hartree, Fock, or Slater determinant? So what's phi prime? Well, I think you can believe on the basis of the rules of determinants that this is equal to the old Slater determinant phi multiplied by the determinant of the matrix C. Now, the determinant of the matrix C we're assuming is non-zero because we want nonlinear combinations. And the result is the new Slater determinant is just a C number multiple of the old one. Those two Slater determinants differ by a normalization and a phase, and therefore physically represent the same state. So what this means is that forming such linear combinations from a physical standpoint, all it changes is the normalization and phase of the final state. And so physically it doesn't change anything. So minimizing the energy is not going to be able to distinguish between these orbitals lambda and the orbitals lambda prime. This is a way of saying that all that the minimization is going to be able to determine is the subspace of the single particle Hilbert space, which is spanned by these orbitals. And that the orbitals themselves form a basis in that space, but we cannot expect there to be a privileged choice of basis. Now there's a huge number of bases in any such subspace. Just by changing the matrix C, you get different versions of them. We're not going to try to narrow this down to a single choice of basis, but what we will do is narrow it down to at least orthogonal bases. So in the single particle Hilbert space, we can imagine there's some subspace like this. So if this is the single particle Hilbert space, let's call it E for a single particle. There's some subspace in here. Maybe if there were two electrons, it would be a two-dimensional subspace. So let's require that the single particle orbitals U1 and U2 form an orthonormal basis in that space. This is a way of saying that without loss of generality, which is what WLOG stands for, we can assume that the single particle orbitals lambda and mu are orthonormal. The scalar product of lambda mu is Kronecker delta lambda mu. Now I'll remind you that in the Hartree theory, we only required that the orbitals be normalized, not that they be orthonormal. And in fact, I don't know if I said this, but let me go back to Hartree and mention this. is that the orbitals u lambda that emerge, they're normalized because we force that by the Lagrange multipliers, but they're not orthogonal to one another. And the reason is that they're eigenfunctions of different Hamiltonians. Each orbital has a different Hamiltonian because it's got a different V lambda. In other words, the one self-interaction term, which is excluded, depends on the orbital in question. So they're eigenfunctions of different Hamiltonians, and they're not orthonormal to one another. Now, whereas in Hartree-Fock theory, what we're finding is that, in fact, there's only loose conditions imposed on the orbitals, but there's no loss in generality in assuming that they are orthonormal. And this is what we shall do for the Hartree-Fock theory. This is one place where Hartree-Fock theory is actually simpler than the Hartree theory. It's not the only one. All right, now then.
Professor?
Yes.
I'm sorry I asked you to repeat yourself, but could you just explain one more time what the phi prime is?
Yeah, so phi prime is a Slater determinant that's constructed out of the lambda primes, which are just linear combinations of the lambdas. So I mean, these are really orbitals we're multiplying together. That's like multiplying wave functions. So in that sense, you can think of it as like multiplying numbers. So if I did this, if I had a determinant like this, and I formed linear combinations like this of these lambdas that were being multiplied, you'd see by the rule of multiplying determinants that it's just the new determinant is the product of the old determinants. Does that make sense? I didn't go into detail, but I think that's fairly clear.
Yeah. So you're kind of trying to combine all of the like orbitals?
No, what I'm trying to do is to address whether or not the orbitals are unique, and this shows that they aren't. Because if I had some set of orbitals lambda and then I replace them by non-singular linear combinations of them, I would get the same physical multi-particle state. And therefore the expectation value of energy would be the same. And therefore minimizing the expectation value of energy can't tell the difference between the original orbitals lambda and the new ones lambda prime. And
okay.
that's a way of saying that the minimum energy or minimizing the energy is actually determined only by the subspace of the, it's an n-dimensional subspace, so the single particle Hilbert space, which is spanned by those single particle orbitals.
Okay.
And so, we might as well choose an orthonormal basis in that subspace, and that's what this condition is.
Okay.
All right.
Yeah, thanks.
By the way, when I say single particle orbitals, that's really redundant because by orbital, I mean a single particle wave function, but I say it anyway because I want to emphasize that these are single particle and they're not the multi-particle wave functions.
Okay. Thank you.
All right. So this is some background then on Slater determinants and the orbitals that go into making it up in terms of which they are expressed. All right, now then, the time then has now come to start talking about permutations. So let me do that. Let me start here. To save paper, I'll start at the bottom of this page. So I will define a permutation. You know, I've looked at a lot of quantum books on permutations, for everything from, you know, Wigner's book on group theory to, you know, all the books that I can find. And nobody ever defines a perturbation. They say, oh, it's a rearrangement of objects. Okay, they don't ever actually define it. Okay, so I'm going to define a permutation. A permutation is a map from the first set of n integers 1 through n, that's the ones we're interested in here, into the same set of integers 1 through n, which is required to be invertible. And I'll use the symbol capital P to stand for the permutation. So it's really just a function that maps integers into integers, but it does so in an invertible way. So that means the function is 1 to 1. And therefore, for every integer in this set, there's an associated integer, which is the value of the function inside the same set. And because it's 1 to 1, there's no overlap. And so every target integer over here has a unique pre-image. That's the way of saying the function is invertible. And that what that means is the function amounts to a rearrangement of the first n integers. So if n is an integer, let's say between 1 and capital N like this, then we'll denote the value of the function p on n just by saying p of n. It's kind of an obvious notation because that's what p is as a function. But I'll also write it as p sub n if I'm feeling that way. It's just, it means the same thing. All right. So that's what a permutation is. Now, in order to specify a permutation, you can just tabulate it as a function. We can have n on one side and p of n on the other, like so. So if we have a permutation of three numbers, 1, 2, and 3, we might have 3, 1, 2 could be the value of P of n. This would specify a permutation. Another notation I'll use for specifying the same thing is basically the same idea, but I'll put the ends on the first, I'll write it horizontally instead of vertically. And I'll put 1, 2, 3 along the top row. That's the n value. And then I'll put the P of n's at the bottom, 3, 1, 2. And you can think of this by saying that, so if this is P, if P is equal to that, you can think of P maps 1 into 3, it maps 2 into 1, and it maps 3 into 2. That's the mapping is indicated here by those numbers. So let me take that same permutation here, 1, 2, 3, and 3, 1, 2, just to continue with that same idea. We get the same permutation if we rearrange the columns. Suppose I write it in the order of the upper column is 2, let's say 2, 1, 3. Well, 2 gets mapped into 1, 1 gets mapped into 3, and 3 gets mapped into 2. So these are actually the same permutation because they specify the same map. It's just a way of writing this. By the way, if I want to take the inverse of this permutation, 1, 2, 3, 3, 1, 2, how do I do it? Well, I just turn it upside down, 3, 1, 2, 1, 2, 3. So this now says that 3 gets mapped into 1, 1 into 2, 2 into 3. That's the inverse of what the original one did. If I want to rearrange the top row to put it in order, I'd have 1, 2, 3 in the top row. And you should see 1 gets mapped into 2, 2 gets mapped into 3, and 3 gets mapped into 1. So if this is the original P here, then this is no, I didn't say that right. Let's do this right. These two are the same because I just rearranged the columns. This is the same permutation again, so that's P. What I meant to say, if P is equal to this, then P inverse is equal to that. That's where we just put this, just swap the two rows. So this is also P inverse. So if P is 1, 2, 3 over 3, 1, 2, then P inverse is 1, 2, 3 over 2, 3, 1. Okay, it's like that. All right, those are the inverse permutations. By the way, permutations can be multiplied. If P and Q are two permutations, then the product of P with Q is just the composition of the functions. So P composed with Q as a function of n just means P of Q of n. That's all it means. Composition of functions is automatically associative, so the multiplication rule is associative. It's not, however, commutative. In any case, with this rule of multiplication and the set of permutations, of which there are n factorial, because there's n factorial ways of rearranging the numbers, forms a group. The group elements, there's an identity, which is just the identity. The identity permutation is obviously just 1, 2, 3, 1, 2, 3. Every permutation has an inverse. There's a multiplication rule. It's associative. That's what you need to make a group. All right. In any case, that's some notation about permutations. Now, let's see a couple other things about permutations. There's a special kind of a permutation called an exchange. Let me illustrate an example of this. Let me talk about the exchange E24. And let's suppose we have 5 objects here. 1, 2, 3, 4, 5, like this. So what E24 does is it just swaps 2 and 4. I think the notation is clear, and it doesn't do anything to the others. 1, 3, 5 don't change. So this is a long way of writing out E24. I think this example explains what the exchanges mean. Not every permutation is an exchange. This one up here is not, but every permutation can be written as a product of exchanges. So let's take this one, for example. Let's take 1, 2, 3 times 3, 1, 2, like that. And let's call that P. And I'd like to show you how you can write this as a product of exchanges. Let's look at the first column. It maps 1 into 3. What I want to do is fix that up so it maps 1 into 1. So what I'm going to do is to take this P and I'm going to multiply on the left by the exchange 1, 3, E13. And what is that? Well, I'll put the 1, 2, 3 in the first row. So this is multiplying, first carrying out this permutation and then following it by the E13 permutation. First one maps 1 to 3. And then E13 maps 3 back to 1. So the 1 goes to the 1. That's what I wanted. That's why I set that up, is to make that first column straighten it out. Now P maps 2 into 1. And then the E13 maps 1 into 3. So I get a 3 there. And 3 maps, and the P maps 3 into 2. And the E13 doesn't do anything to that. So the 2 stays there. So this is the product E13 times P. It's not the identity, as you see, but the first row has been straightened out. First column, excuse me. Now to fix up the second column, we'll take this and we'll multiply it by E23, E13, P, like this. Let me put parentheses around this. And what's that equal to? 1, 2, 3. Well, the E13P is this thing here, because that's what this was, is E13. So 1 goes to 1, the E23 doesn't do anything to that, so that stays the same. The 2 goes to the 3, then the E23 changes it back to a 2 again. The 3 goes to a 2, and the E23 changes back to a 3. And so what we see is this is equal to the identity. So what we get is E23 times E13 times P is equal to the identity. And that means that this product of exchanges is equal to P inverse. So if I bring it over to the other side, what I get is P inverse is equal to E13 times E23. I have to read this backwards, and the reason this is that the product inverse of product is you have to swap the orders when you take the inverses. Also, the exchange it's equal to its own inverse, so I don't need to put minus ones on this. Anyway, this may sound kind of complicated what I'm doing here, but the punchline of this is that every permutation can be represented as a product of exchanges, and I've illustrated this here for this particular permutation at the top. This one turned into a product of 2 exchanges. And it's easy to see this applies to any permutation, no matter how complex. So in a sense, the exchanges can be used to generate all possible permutations by multiplying them together. They're the building blocks of permutations. Now, the decomposition of a permutation into exchanges is not unique. There's more than one way to do it. But you'll find that if you do it, no matter how you do it, the number of exchanges required is always either even or else it's odd. And so this allows us to classify permutations as either even or odd permutations, depending on whether their decomposition into exchanges involves an even or an odd number of factors. We call these even and odd permutations. This one in particular is an even permutation. This leads me to define something I'm going to call the parity of a permutation, which I'll denote by minus 1 to the p. Minus 1 to the p is just notation. Here's what it means. It means that this is plus 1 if p is even, and it means that it's minus 1 if p is odd. So this is in effect as the sign, if you will, or I'm calling it parity or sign. Let's call it sign of the permutation, plus or minus 1. All right. Now this sign or parity of the permutation obeys a simple rule, which is easy to see. And that is if I take 2 permutations P and Q, and I multiply their signs together, Q, this is the same thing as the sign of the product PQ. And how do I know that? Well, if I factor P into exchanges and I factor Q into exchanges, let's say Q has 5 and P has 3, then P times Q is a product of 8 exchanges. So that means PQ is even though P and Q separately were odd. And you see that's why it's the product of the minus 1 to the P times minus 1Q. It's kind of obvious if you factor in exchanges. In any case, this is an important rule or basic property of the sign or parity of a permutation. Okay, so that's one of the rules of permutations, is its sign or parity. Okay, those are the main things that I want to say about permutations as mathematical objects. These are just functions. Let me now say something about permutation operators in quantum mechanics. We're going to be interested in systems with identical particles. Let's say initially we have a system in which all the particles are identical. It's easy enough to generalize. In fact, in general, a system has various species of particles in which, in general, there are multiple copies of each species. So in that case, the kinds of permutations one is interested in are permutations within each species. So for example, the helium atom has 2 identical electrons orbiting the nucleus. The nucleus has 2 identical protons inside of it and two identical neutrons as well. And so there's three different species of identical particles. And the symmetrization postulate, which we talked about before, concerns the exchange of identical particles of any given species. In a given system, you may have different ways of doing that. Some species may be bosons and others are fermions, in which case you've got an exchange rule for each different species. But for today, right now, tonight, we're really thinking about a multi-electron atom, so we're thinking about electrons. So let's just talk about a single species. I think it'll be pretty clear how to generalize it later if you want to do that. So let's talk about a collection of identical particles. Let me begin with a single particle Hilbert space, which I'll just call single particle Hilbert space, which I'll just call script E, like this. And this, I won't say what this is. This is a single particle Hilbert space. Let me introduce a basis for this space. This basis is a collection of state vectors I'll call X here, like so, where X is equal to some collection of quantum numbers. Could be one quantum number, it could be more than one. For example, it could be, in a central force problem, it could be NL, M sub L, and M sub S, the four quantum numbers, including the magnetic quantum number for spin, for a central force wave function or basis function. That's a possibility for what X could stand for. So X runs over all possible values of these quantum numbers, producing a basis for the single particle Hilbert space. Now let me define the total Hilbert space for the n particle system is given by the n copies of the single particle Hilbert space, one for each particle, which I'll write like this, as a tensor product of these single particle Hilbert spaces, one for each particle. And again, these parenthesized numbers are the particle labels here as I was using before in a different notation, different context. That's what that's for. So it's just a tensor product of a set of n copies of identical Hilbert spaces. And we can use an identical basis in each one of those Hilbert spaces. And so the basis for E total, what is that? That's a collection of basis vectors, which are just the products, x1 for particle 1 times x2 for particle 2, out to xn for particle n, like so, where each of these x's 1, 2, 3, and so on run over the same set of values. In other words, we take all possible combinations of quantum numbers of values of x for each of the particles, and we assign them to these states here and run over all possibilities, and that multiply those state vectors together, really tensor product them, and that creates a basis for the total Hilbert space. This total Hilbert space, by the way, is also something I've called previously the nominal Hilbert space, and so I'll call it that as well. By the nominal Hilbert space, what I meant is the collection of wave functions you'd get if you didn't care about the symmetrization postulate. And that's the stage I'm at here. I don't care about it right now. So total and nominal here actually mean the same thing in this discussion. But in any case, this is the basis for this. Now, if P is a permutation then of the n integers 1 through n, I'm going to associate this with a unitary operator I'll call U of P that acts on the Hilbert space. And U of P is defined this way. It acts on the product basis state x1 for particle 1 out to xn for particle n, like so. It acts on that basis state, and it produces the basis state, which is x sub p sub 1. Excuse me, make a cat here. X sub p sub 1 for particle 1 out to x sub p sub n for particle n. And if this is supposed to be a vertical line. So if we do this, you see it maps the basis vectors into themselves simply by permuting the labels of the single particle labels, for example, here, the set of quantum numbers amongst the different electrons. Permutes them, that's all it does. Now, at a certain point, I'm going to get lazy, and instead of writing U sub p, I'm just going to replace it by p, thereby confusing the permutation as a map of integers onto itself with the corresponding unitary operator. It saves writing to do that, and if it won't confuse you, then I will do that. So this is how a permutation operator acts on these basis states. Now then, by linearity, since any state in E total can be represented as a linear combination of these basis states, this defines the permutation operator on E total. And one can show that the result actually doesn't depend on the choice of basis states, single particle basis states that were used in the construction. It's actually independent of that. So this then in brief is the explanation of the definition of the unitary permutation operator acting on quantum states. All right. Now then, having said all of that, maybe this is a time to pause because I've already said quite a few things. So let me pause and ask if there's any questions about that. I'm kind of systematically building up properties of permutations. Any questions about this so far?
Yeah, sorry. I feel like this might have been asked before, but can you explain again what the one inside the ket and the like one
This one here?
superscript, how are they different? Yeah. And then the superscript one, how are they different?
Well, the superscripts indicate the electron. So this is the first electron, that's the last one, or the particle. As I say, these are particle labels in the parentheses. And what the X1 does is this just stands for a choice of the single particle quantum numbers that specify basis state. So this is saying you can have any one of the basis state. There's usually an infinite number of them. Any one for particle 1, any different basis state for particle, a different one for particle 3, and so on. That gives you a collection of n of them, n of these x's. And each of these x's ranges over all possible values of the single particle quantum numbers. Does that make sense? That's a way of creating products of all possible basis states of all possible single electron states.
Okay, thanks.
Okay, and that gives you the basis for the multi-particle Hilbert space. All right, and this shows what permutations do to it. Now, we know that the total, or what I also call the nominal Hilbert space, is not the physical Hilbert space because of the requirements of symmetrization. We gave a version of the symmetrization postulate in a previous lecture, and I'm going to rephrase it now in terms of permutation operators. The expression for the requirement depends on whether the particles are bosons or fermions, and I'll give them both to you. So it works like this: is that we'll say that a state psi, which is contained in the nominal Hilbert space, is physical. That is to say, it actually belongs to the physical subspace, i.e., psi actually belongs to the physical subspace, E physical, if the following is true, is if we apply a permutation operator to psi, what we get back is we get psi itself if there's identical bosons, and we get -1 to the p times psi in the case that there's identical fermions. Now, you'll recall that in the earlier expression of the symmetrization postulate, we said that boson states were symmetric under exchange of any two identical bosons. Well, since permutations are built up out of products of exchanges, the fact that p psi gives you psi is really the same thing. Exchanges are permutations, so it includes that as well. In the case of fermions, we said if we exchanged any two identical fermions, you get a minus sign. Well, the permutation again can be factored into exchanges. So there's going to be a collection of minus signs, which is the number of exchanges. But that's exactly what this -1 to the p is. It's the product of the number of exchanges. It's either +1 or -1. So in fermion states, you can get a +1 if your permutation is even. All exchanges are, however, are odd, so they always give you a minus sign. In any case, there's nothing new in this. It's just a reformulation of the symmetrization postulate now from the standpoint of permutations. By the way, if you had a system that had multiple species of identical particles, some fermions and some bosons, then the rule that you would state is that the p operator here has to be restricted to permutations of particles of one species. Now, you can take different species at a time. You can do the bosons first and then the fermions later, or the electrons first and so on. Take them one species at a time. But within a given species, let p be a permutation within a given species, then the rules, as I've stated here, are just the same. So that's how you generalize it to systems with multiple species. Now, you may recall when we talked about the symmetrization postulate before, that the whole notion, or this whole approach to the subject, gives rise to the notion of states that are physical and states that are not physical. A physical state is one that satisfies the symmetrization postulate, and therefore belongs to the physical subspace, which is the one that's properly symmetrized or anti-symmetrized. Whereas a non-physical state is one that does not belong to the physical subspace, but it might be some other vector, either here an E total or otherwise I call it E nominal. It means the same thing. So it's just a wave function that's not properly symmetrized or anti-symmetrized. I also pointed out that we have the concept of physical and non-physical operators. And a physical operator is one that doesn't map you out of the physical subspace. That will be the case if it commutes with all exchanges. But if it commutes with all exchanges, it commutes with all permutations as well. So if K is a physical operator, if K is physical operator, then K commutes with all permutations equals 0 for all permutations P. And in the system that we're considering of our multi-electron atom, it turns out that not only the Hamiltonian, but actually the two terms H1 and H2, which comprise the Hamiltonian, are individually physical operators because they commute with exchanges or permutations. You can see that quite easily because H1 is the sum on I of single particle Hamiltonians, lowercase h sub I is equal to pi squared over 2 minus z over ri. That's the notation I'll use right here. But clearly, if I do a permutation, it just rearranges the terms of the sum and doesn't change the sum itself. Whereas H2 is a sum on I less than j of 1 over rij. And again, this is invariant under permutations of electrons. For example, if there were 3 electrons, it'd be R1 1 over R12 plus 1 over R13 plus 1 over R23, if I can say it while I write it. And this is invariant under any permutations of the three electrons. So H1 and H2 are actually individually physical operators. So also is the total orbital angular momentum of the system, the sum over the electrons I equals 1 to n of the L sub i's, although the individual L sub i's are not. And the same thing would apply to the spin. The total spin of the system is physical, and the individual spin sub i's are not physical, and so on. All right. So this is a distinction between physical and non-physical operators. All right. Now, given that we have this nominal Hilbert space, which I'll call E nominal, it's the same as E total, and there's a subspace of that, which is E physical, there's some convenience in having a projection operator, a projector, which will project onto the physical subspace. I'm going to deal with this only in the case of fermions, which is what we're interested in for atoms, because those are electrons. Let's talk about the projector onto the physical subspace. I'll call this projector A. A stands for antisymmetric. This is the antisymmetric projector, and it'll take any vector in the nominal space and project it down. It turns out the expression for A is the following. It's 1 over n factorial, the sum over all permutations, of which there's n factorial of them, of the sign of the permutation minus 1 to the p times the permutation itself. And this p here really means u of p, because these are the operators that act on the Hilbert space. So this anti-symmetrizing projector then is a projection operator, which I claim projects onto the physical subspace. Now, this is actually quite a useful object, and I'd like to prove some of the statements I've made about it. So there's a couple of things I want to prove here. One is that A is a projector, and that's the first thing to say. And then the second one is to say that A projects onto E physical. And this is for the case of fermions only. There's a similar construction. There's a symmetrizing projector that applies for the case of bosons. We can worry about that later. All right. So to show that A is a projector, we need to do two things. We have one A, which is to show that A is Hermitian. And then the second one is to show that A squared is equal to A. This is our definition of a projection operator. So let me show you that these are true. So in the first place, to show that A is Hermitian, what we have is that A dagger from the formula up here is 1 over n factorial, by the way, sum on permutations P. And then we have minus 1 to the P. And then we have P dagger like this. I didn't mention this, by the way, but these operators, which I at first called U of P, as the notation indicates, are unitary operators. So U of P inverse is the same thing as U of P inverse like that, which is, since they're unitary, is the same thing as U of P dagger. These properties are all easy to show based on the definition of these operators. So A dagger is equal to the sum on P of minus 1 to the P times P dagger, where P dagger means the dagger of the permutation operator. But P dagger is also the same thing as P inverse. And by the way, the sign of a permutation is the same as the sign of P inverse. Pretty easy to see if you just invert a string of exchanges. So that P can be replaced by P inverse. So if I put P prime is equal to P inverse, then this becomes 1 over n factorial times the sum on P of minus 1 to the P prime times P prime. Now it's fairly easy to show and easy to see that if you take the list of permutations and then you replace it by each permutation by its inverse, you get the same list all over again, but just in a different order. That's because some permutations are equal to their own inverse. The exchanges are that way. So they just get replaced by themselves. And if they're not equal to their inverse, then there's a P and a P inverse, and they just swap places when you replace them by inverses. So the whole list of permutations is just the same list, but in a different order. So summing on P is the same thing as summing on P inverse. So I can replace this P by P prime. Now P prime then is a dummy index, and you see that this is A all over again. So although the individual permutation operators in general are not Hermitian, in fact they're unitary. They're unitary definitely. They're usually not Hermitian. Exchanges, by the way, actually are Hermitian, but the other permutations aren't. Nevertheless, this sum over all the permutations here with these signs in here gives us an overall operator which is Hermitian. So that takes care of 1A, is that A is equal to A dagger. Now, this should have been 1A and 1B, not 1A and 2B. All right. Now, the next thing I want to show is a little lemma here, if you want to call it that, little lemma. It says the following, is that if Q is a permutation, let's take minus 1 to the Q times Q. That is to say, the sign of Q times Q. And let's multiply it times A. And the claim is that's equal to A itself, because A all over again. And the proof of this just comes from multiplying this out. This becomes let's write it this way, it becomes equal to 1 over n factorial from the sum on A. And then I have the minus 1 to the Q times the sum on P of minus 1 to the P times P. And the 1 over n factorial is out here like this. And then the minus 1 to the Q is just a number, combines with the minus 1 to the P. So I get a sum on P here of minus 1 to the QP. And then permutation P times Q times P is QP like this. All right. Now then, here I'm going to do a similar trick that I used before. Let's let P prime is equal to QP. So this sum then becomes equal to 1 over n factorial times the sum on P of minus 1 to the P prime times P prime. Now the argument is very similar to what I used before. If I take the list of permutations P and I multiply the list on the left by a fixed permutation Q, this gives me the same list all over again, but in a different order. So summing on P prime is the same thing as summing on P, and I can put a prime there. And if I do, then this by dummy summation of index of summation, this is just A all over again. And that proves my lemma here, right here, that this is equal to that. Okay. Now then finally, I want to prove that A squared is equal to A. That's the second part in showing that A is a projector. Let's do that. So A squared is equal to obviously A times A. So let me write it this way as the sum on Q, let me write it as sum on P minus 1 to the P times P. This is divided by n factorial. That's the first factor of A. And for the second factor of A, I'll just write A like that. On the other hand, by my little lemma up there, this minus 1 to the Q times A is equal to A with Q replaced by P. Minus 1 to the P times A is just A all over again. So this is 1 over n factorial times the sum on P of just A. Now what I'm summing is n identical terms, n factorial identical terms, because that's P runs over n factorial elements. So this sum is equal to n factorial times a. The n factorials cancel and the answer is equal to a. And so this proves then that a squared is equal to a, and we would have therefore now shown that a is actually a projector. Okay. Now then, so that's good. Now the next thing to do is to show that it actually projects onto the physical subspace. Let's let psi be any state in the nominal Hilbert space. And let's let phi, capital phi here, be -1 to the p times p acting on psi. And no, I'm sorry. Let's let phi be this is equal to the anti-symmetrizing projector applied to psi. We claim it's an anti-symmetrizing projector. I want to prove that it is. To prove that it is, I need to show that this state phi belongs to the physical subspace. If it belongs to the physical subspace, then the anti-symmetrizing projector doesn't do anything to it. Or let's just go back to the symmetrization. So let's do this. Let's take -1 to the p times p and apply it to phi. So let's consider this. Because to test if it's a physical or not, we need to see what a permutation operator does to it. But this is -1 to the p times a acting on psi. By our little lemma, that's the same thing as a acting on psi. And that's the same thing as phi. So putting this together, if I bring the phase factor over the other side, we get p acting on phi is equal to -1 to the p multiplying phi. And we see that indeed the projected state actually is physical. So this is not only a projector, it's the physical projector onto the anti-symmetrizing subspace. Okay, those are the main properties of permutations that we need and their projectors and so on. And now we're ready to get down and actually do some Hartree-Fock theory. So let's work on that. Any questions about this before I go on? Now, if we go back to the Slater determinant, I'm afraid I've erased it already, but let me write it out. 1 over n factorial. I had a square root of n factorial in there. And then we had these orbital 1 for particle 1 through orbital 1 for particle n, down through orbital n for particle 1, down through orbital n for particle n. That was our Slater determinant, and this was the Hartree-Fock state, which we called phi. I'll call this HF state here, because I've been using phi for something different in the interim. Anyway, this is the Hartree-Fock state phi.
Professor, sorry, the paper shifted. We can't see.
Yeah, thank you. Thank you for telling me that. So this is just to repeat the Slater determinant, as well as the definition of the Hartree-Fock trial wave function. Now, expanding out this determinant involves n factorial terms in which the orbitals have been permuted amongst all the electrons in all the different possible ways, and moreover multiplied by plus or minus ones, which are the signs of the permutations. Well, that's the same thing, except for the factor of n factorial. That's the same thing as the anti-symmetrizing projector. In fact, this is the same thing as the square root of n factorial times the anti-symmetrizing projector applied to the state 1, orbital 1 in particle 1, orbital 2 in particle 2, ... out to orbital n and particle n, like so. That's just in essence, that's just the definition of the Slater determinant. The anti-symmetrizing projector had a 1 over n factorial in its definition. It was defined over here, you see, whereas the Slater determinant's got 1 over root n factorial. That's why we get a square root of n factorial there. Now this state, which is represented over here, is the Hartree state, which I called phi Hartree. Looky there. This is just the orbitals distributed amongst the electrons in ascending order. And so we get now a connection between the Hartree-Fock state and the Hartree state. In fact, the Hartree-Fock state, which I'll call phi without an h, is the square root of n factorial times the anti-symmetrizing projector times the Hartree state. Let me box that because that's very convenient. That just tells us that if we project the Hartree state onto the antisymmetric subspace, we're going to, first of all, screw up the norm. That's why we need the square root of n factorial there to renormalize it. That makes phi normalized. But except for that, it's just the antisymmetrized version of it. All right. Now then,
Professor,
yes.
can I ask a question about something a little bit earlier?
Yes, indeed.
You were talking about the physical Hilbert space, and so that is not the same as like the Hilbert space of like observable Hermitian operators, right?
Well, no, because the Hilbert space is this normally we mean the Hilbert space of wave functions, whereas operators act on wave functions.
Oh, okay, right. So we're looking at wave functions, but you were okay. So maybe I'm just confused because you were talking about different operators being physical.
Yeah,
And
so
like,
an operator is physical. So a wave function is physical if it's properly anti-symmetrized. So that's what I'm saying when it belongs to this physical subspace. An operator is physical if it maps a physical state into it, if it maps the antisymmetric, properly anti-symmetrized subspace into itself. That's required of a physical operator. It must give you a physical answer to a physical input.
okay.
Okay. And in particular, the H1 and H2 terms in the Hamiltonian are physical. They do commute with all permutations. So
Okay.
also does the total orbital angular momentum, total spin angular momentum parity does, but some other operators do not. Operators that refer to individual electrons like L1 or the coordinate X R1 or X1, whatever you want to call it, of electron 1, those are non-physical.
Oh, okay. So when you were saying like L sub I and S sub I were not physical operators, you weren't saying like LZ and SZ, you were saying like the L vector operator for like
Yeah, I mean the operator L for electron I.
Okay, that makes sense.
Yeah,
Okay.
and it's not physical because the real state has got all orbitals permuted amongst all the electrons.
Okay, I
So
see.
if you're using wave functions to describe states, which we're doing here, there actually are ways of doing this without doing that. We'll get to that. But if you're using wave functions to describe states, there's no way to write down a multiparticle wave function, even for identical particles, without labeling the particles. You have to talk about electron 1, electron 2.
Mhm.
However, none of the physics can depend on that labeling.
Mm.
And that's what working with these physical subspaces does for us.
Okay.
Okay.
Okay, thank you.
All right. So anyway, this is a neat formula now connecting Hartree theory with Hartree-Fock theory. This is the Hartree theory here. Hartree, sorry, my handwriting's messy there, but that stands for Hartree, which is convenient because the Hartree trial wave function is much simpler than the Hartree-Fock. All right, now let's compute some expectation values. One of the things we're going to need is the Hartree-Fock state, which I'm just calling phi sandwiched around H1. Based, however, on this formula up above, if I plug this in as a bra and a ket, I'm going to get 2 factors of root n factorial, so I'm going to get an n factorial. Then I'm going to get phi Hartree on the left. I'm going to get the anti-symmetrizing projector A dagger, H1, A, like this, phi Hartree. So this reduces a Hartree-Fock a scalar product into a Hartree scalar product, or matrix element. Excuse me a second. Yeah, excuse me just a second. Yeah, okay, fine. Now, so that turns out is quite convenient. Now, not only that, we just showed that A dagger is equal to A because A is a projector. And A, moreover, is a linear combination of permutation operators, and H1 being physical commutes with all of them. So A commutes with the anti-symmetrizing projector as well. So this product of 3 operators here turns into A H1A, which turns into H1 times A squared. But since A is a projector, that's the same thing as H1 times A. So we can simplify that operator in the middle. And this thing then turns into n factorial times phi Hartree sandwiched around H1 times A times phi Hartree. Now the H1 is a sum on I of single particle Hamiltonians I'll just call lowercase I for brevity. And the A, to remind you, is 1 over n factorial, sum over permutations minus 1 to the p times p. You can see the 1 over n factorials will cancel there. This is going to turn into two sums then. We have a sum on I from here. We have phi Hartree. Let me write that out explicitly. That's going to be orbital 1 for particle 1 out to orbital n for particle n as bras, because that's a bra there, phi Hartree. H1, what did I have here? Did I have, is this sum on I here? Yeah, let me do it right. There's going to be a sum on I coming from this sum here on the Hamiltonian H1. There's going to also be a sum on permutations coming from the A and a minus 1 to the P. So I'll take that into account. Now let me go back and do the phi Hartree bra. That's bra 1 for particle 1 out to bra n for particle n, like so. Then we have the HI operator, which I'll write out explicitly as pi squared over 2 minus z over ri. And then what we've got is the permutation p applied to phi Hartree, which is orbital 1 for particle 1 out to orbital n for particle n. But permuting phi Hartree like this is the same thing as giving orbital p1 for particle 1 out to orbital pn for particle n. Okay? Again, let me just abbreviate this and call this h sub I. So this is what we get. Now then, to understand this, let's take an example. Let's take, for example, the case I is equal to 2. Then we get a term that looks like this. We're going to have orbital 1 for particle 1 out to orbital n for particle n. We're going to have H2 in the middle. Then we're going to have orbital P1 for particle 1 out to orbital Pn for particle n on the right. Okay. Now H2 depends on the coordinates and momenta and spins of only particle 2. So the bra for particle 1 here and the bra for particle 1 over there on the two sides just shine right through that. They don't see it at all. And they therefore combine together by the orthonormality. Remember, our orbitals are going to be orthonormal now, and because this is Hartree-Fock theory. So they're going to combine by orthonormality and give us a Kronecker delta 1p1 from those. The same thing will apply for electron 3, 4, 5 all the way out to n, not 2, but all the others except for 2. So we have Kronecker delta 3p3 out to Kronecker delta npn like this. All right, for all the orbitals, and only thing that's going to be left is the bra and the ket for particle 2. That'll be multiplied by bra 2 for particle 2, H2 in the middle, and then ket P2 for particle 2. So that's what this turns into. Okay. Now, on the other hand, we're summing over all permutations. There's n factorial terms. That's a lot of terms. But these Kronecker deltas are going to severely restrict which permutations are allowed. If I write out the permutation this way as 1 out to 2, 3 out all the way out to n, like so, then these Kronecker deltas force 1 to be P1 to be mapped into 1. P1 is 1, P3 is 3, all the way out to n. The only one that's not forced by the Kronecker deltas is 2. It gets mapped into P sub 2. So of this summation over n factorial terms, the only one that's going to survive is the one that looks like this. But in fact, the only permutation that looks like this is one where P2 is equal to 2. And that means the permutation P itself is the identity, and its signature is equal to +1 because the identity is an even permutation. And so in fact, what this, when I take into account this sum over permutations P, what this whole thing turns into then is just orbital 2 for particle 2, H2 in the middle, and orbital 2 for particle 2 as a ket on the other side, like that. And the result is that the sum over P goes away, the sum over I is still left, and we end up with we end up with a more complicated calculation than in Hartree's case. But believe it or not, the answer turns out to be the same. Is that the Hartree-Fock state sandwiched around H1 becomes equal to a sum on lambda equals 1 to n of these integrals I lambda. Now here I went through there's some steps that I skipped in this, but they're the same steps that I presented earlier in the Hartree theory, because these are now, I mean, if I were to write an earlier version of this, it would be the following: we sum from I equals 1 to n of orbital I for particle I, h sub I, orbital I for particle I. And if you fix this up using our rules for Latin and Greek indices and then write it out as an integral, you find that r sub I is a dummy variable. And you come back to the integrals in my integral table. Let's see, do I still have it here? I did not mean to throw it away. Here it is. Here's the table of integrals. It's this integral I lambda. I lambda is the expectation value with respect to orbital lambda. It's just a spatial part of the kinetic energy and the potential energy of interaction with the nucleus. And this sum that we get here is just summing these over all the orbitals. It's physically plausible that that should occur in an accounting of the energy of the system. And it's the same thing that occurred also in Hartree's theory without any change. So in spite of all the asymmetrization and all the rest of that didn't change. Now then, what about H sub 2? H sub 2 is more complicated. Phi H sub 2, phi. We can analyze this in a similar way. This is going to turn into phi Hartree H sub 2 anti-symmetrizing projector times phi Hartree, like so, times an n factorial, which I forgot. And if we expand out H2, which is a sum over the interparticle interactions, and expand out the A, which is a sum over projectors, the n factorials cancel. This turns into a sum on I less than J, a sum on permutations P, minus 1 to the P is the sign of the permutation. Then for this phi Hartree ket, we have orbital 1 for particle 1 out to orbital n for particle n, the usual thing. Then for the H2, we've got 1 over Rij. That's summed over I less than J to give you the total A2. For the anti-symmetrizing projector, that turns into the minus 1 to the P, which is there. There's the sum on P. And the projector applied to the phi Hartree gives me orbital P1 for particle 1 out to orbital Pn for particle n. Okay. Now then, if we, again, if we took a special case, let's say I equals 2 and J equals 3, like this, in this operator in the middle, that's one particular term of that sum. Then what you'll find is that all of the bras and kets on the two sides combine together by orthonormality, except for particles 2 and 3, because the operator in the middle only depends on the coordinates of those two particles. So you're going to get Kronecker deltas that look like this. You'll get delta 1 P1, delta 4 P4, all the way out to delta n Pn. You won't get them for particles 2 and 3, but all the others you'll get these Kronecker deltas. That means in this sum on permutations, the permutation itself must look like this: 1, 2, 3, 4 out to n, in which 1 goes to 1, 4 goes to 4, and all the rest out here go to n, and P1 and 2 and 3 go to P2 and P3, which are not determined by Kronecker deltas. So once these Kronecker deltas are taken into account, the n factorial sum here reduces to just two terms, which are the two possible values for P2 and P3. Here's what they are. We have P2 is equal to 2 and P3 is equal to 3. That makes this permutation equal to the identity, and that makes the signature that or sign of that permutation equal to +1. The other possibility is that P2 is equal to 3 and P3 is equal to 2. That makes the permutation equal to the exchange of 2 and 3. And -1 to that permutation is equal to -1 because an exchange is an odd permutation. And so what we're going to get then is that I'm taking into account the sum on P, there's going to be two terms that survive. And I'll keep the sum on I less than J. And so the result turns into the following. Let me get these papers out of the way so I can not have the clutter. The result is going to be the following, is that the Hartree Fock state sandwiched around H2 can be written as a sum on I less than J of bra I for particle I, bra J for particle J, 1 over Rij, ket I for particle I, ket J for particle J, like that. That's the first term that came from the identity permutation. Then from the exchange permutation, we got bra I for particle I, bra J for particle J. That part doesn't change. The 1 over Rij doesn't change. But what's left here is the I and J are swapped. We get bra J for particle I, bra I for particle J. Okay. Now then, this first term is the same that we had in Hartree's theory. Involves these integrals, these direct integrals. So this is equal to the first term. And if I switch to Greek indices for orbitals, it looks like this. The first term turns into a sum on lambda less than mu of J lambda mu. Now I'm not done yet. I need to worry about the second term. But as far as the first term is concerned, it's the same as in the Hartree theory. And to go back to my my page of, if I can find it again, my page of integrals, here's what it is. There are the integrals. These are the what we call the direct integrals that appeared in Hartree theory, J lambda mu. I think I explained the physical meaning of them already. It's electrostatic energy. And they appear in exactly the same way, and it's exactly the same sum in the Hartree-Fock theory. What's new is the second term here that involve the exchange. So these are called direct integrals. Those are called exchange integrals. In the second term, one of the things to pay attention to is the fact that these orbitals, if I put them in Latin and Greek form to get the indices straightened out, it'd be a little more clear. But these orbitals have both spatial and spin parts. The operator in the middle, however, is purely spatial. So if I look at the spin part for particle I here, since the orbitals are not the same, the spin parts are not necessarily the same either. So there's a Kronecker delta in the spin parts in addition to a spatial integral. The result is that this matrix element can be written this way as J lambda mu minus K lambda mu, in which K lambda mu, I will write it out down here on our integral page, K lambda mu is equal to, first of all, a Kronecker delta in the magnetic quantum numbers, ms lambda, ms mu. I'll write it that way, times an integral d cubed r prime. And we've got u sub mu of r complex conjugated. I should say, make it u sub lambda. Let's make the first one lambda. U sub mu of r prime complex conjugated. U sub mu of r, u sub lambda of r prime. And this is divided by the Coulomb denominator, r minus r prime. Okay. So this is actually just the same as in the J, except that except there's been a swapping of labels on the kets that were on the right hand side. All right. And these are called the exchange integrals. Now I'll worry about the properties of these integrals. Nope, I won't either because I'm out of time. I see I've run out of time. Let me just briefly mention that this is how it turns out for the expectation value of H2. The fact that the K's enter with a minus sign here means we're going to get a lower estimate for the energy than we had in the Hartree theory. That's good because this is a more sophisticated wave function, trial wave function. And as far as the rest of the physical circumstance or consequences of this, we'll have to work it out in the next lecture. This is Tuesday, right? So it'll be, we'll do this on Thursday. Okay, so that's all for tonight. I know this is a lot of technical stuff. Are there any questions about this? All right. If there's no questions, then I shall stop screen share and turn off the Recording. Let's see here, stop screen share, okay. So I know this is a lot of technical details. Maybe it's too much to go through in all the details in lecture. I did it anyway. It's not hand wavy. We did it legitimately. You can see what's going on. If you follow the logic, you'll see that it's right. We will develop the physical consequences of that in the next couple of lectures. Okay, here we go. Stop the recording.